Okay, everyone, welcome back to our statistics class notes. We're on page 120, which is the last page of our section 8.1 notes. And here we're in section 8.1, we've been talking about the basic idea of performing a hypothesis test. So let's go and do another example, kind of get through all of this and make sure we understand what's going on here with this example. According to census.gov, Duval County is about 30% African American. So suppose you are looking at jury pools for Duval County, each with 400 members in it. So the null hypothesis is that if we're randomly picking everybody correctly, the probability of an African American being selected into the jury pool should be about 30%, right? So that should be 30%. So how many African Americans would we expect on a jury pool of 400 people if the null hypothesis is true? We would expect 30% of the 400, which is 400 times 0.30 or 120. So we should get around 120 African Americans in the jury pool if we're really representing the population correctly. Now let's suppose pool A contains 100 African American people out of 400, and pool B contains 130 African American people out of 400. So which one would have a smaller p-value? So first of all, let's think about this. Assume we're looking at one-side hypothesis test. So 100 is 100 further away from 120, or is 130 further away from 120? So 130 is closer to 120 than 100 is. So just in general, we would say the p-value, which is the probability of getting our test statistic or one more extreme, should be smaller for a test statistic that's further away. And the test statistic, when I get 100 is further away from 120 than 130 is. So let's see how that works. It makes sense, but let's see how it works. So pool A. Remember, the null is that p equals 0.30. 30% of our jury pool should be African Americans. Now, we got a test where we got 100 out of 400, not 130. So we want to see that, is that enough information to say that the alternative is that p is less than 0.30? The true population proportion of African Americans is less than 0.30. So we go through p hat. We get p hat as 100 over 400, which is 0.25. We need our standard error, which is the square root of p naught times 1 minus p naught over n. So p naught's 0.3. Put that in. N is the sample size of 400. Here's your standard error, 0.0229. So your test statistic z is p hat minus p naught divided by that standard error. So 0.25 minus 0.30 divided by 0.0229. So that gives you a z-score of minus 2.18. Now that's going to have a smaller p-value since the test statistic is further from 0. Right? When you convert everything to z-scores, you got 0 in the middle, and your test statistic where p hat was has a z-score of minus 2.18. So I want the area in the left tail there, thinking about a one-side hypothesis test. That's your p-value, is this area in the left tail. Now if I look at the situation where I had 130 out of 400, which is more than 30%, I'm going to do a one-sided right test. Right, I want to do the alternative is that p is greater than 0.30 to see if that's the case. So I work all this the same. The standard error is still 0.0229 because it's using the same calculations. We use our 0.30 for p naught. We get the same standard error. The test statistic will be different because our p hat now is 0.325 minus p naught, which is 0.3 divided by the standard error. So that's a z-score of 1.09. Now 1.09 is not nearly as far away from 0 as negative 2.18 is. Just like 25% is farther away from 30% than 32.5% is from 30%, right? Okay. So you get a p-value that's bigger, the area in the tail outside that test statistic. In other words, probably getting that test statistic or one more extreme. They're probably getting z equals 1.09 or one more extreme. In other words, the probability of z being greater than or equal to 1.09 is this p-value. But you can see from the pictures, I tried to be somewhat precise. This has a larger p-value because the z-score, the test statistic, is closer to 0 than the test statistic in this problem.